All right. Hello, everybody. Today we're going to be going over Chapter 3 of Classical Dynamics of Particles. And we'll see how far we get. I'm trying to aim for a 45-minute video since I have something to do, so I might not be able to get through the entire chapter, but hopefully we can get to 3.6 is kind of my goal. So, okay. Let's get into it. So, first of all, first up is the introduction, where they basically just talk about the general equation for a Taylor series, which is basically something that can be expanded. F of x is equal to f naught plus x df dx plus 1 over 2 factorial. By the way, this is centered at x is equal to 0. Like x naught is equal to 0 if you've seen other formulations of this, which is written by this notation right there, where the derivative is taken with respect to x at 0. But anyways, that's the Taylor series. I apologize by my terrible handwriting. Hopefully it'll be better as time goes on. But anyways, we want to basically find forces basically that have the relation f of x is equal to negative kx, which you've probably seen this as Hooke's law or spring stuff and physical stuff, because the point of this chapter is oscillations. So, okay, let's get into 3.2, which is the simple harmonic oscillator. 3.2. So this is a problem you guys have probably seen in your lower division classes. Oscillator. Okay, so we can use Newton's second law. F is equal to ma. And we get our force is negative kx, and that's equal to mx double dot ma, right? So we can define the frequency, the fundamental frequency, or omega naught, as omega naught squared is defined as k over m. So we kind of just took m and brought it over to this side, so we have basically negative omega squared x is equal to x double dot. So therefore we have x double dot plus omega naught squared x is equal to 0. Now, this has a solution, but before we go into the solution, what I want you guys to notice is that we start off with x, and this is true for a lot of ordinary differential equations, is that we have x, and we kind of just get back to it. I'm sorry, we have x double dot, so second time derivative of x, we can get back to it. In other words, we need to find a function that when we take the derivative of it twice, we get the function back with, some other constant in there that we don't really care about. And functions that do that are sinusoidal. So we have basically two solutions for this, which is x of t is either equal to a sine of omega naught t minus some phase delta, or x of t is equal to a cosine of omega naught t minus some other phase phi. Okay, where delta and phi differ by pi over 2. In other words, it's a sinusoid. And we can double check that. First derivative of sine is cosine. Second derivative of sine is negative cosine. So there you go. So you get the same function back. But okay. So now we can kind of talk about the kinetic energy for an oscillator, which is T is equal to 1/2 mx dot squared, which is equal to 1/2 m omega naught squared a squared, if we choose sine as our x of t, cosine squared omega naught t minus phi. Okay, and that's just equal to 1/2 k a squared cosine squared omega naught t minus delta. Sorry, phi, whatever you want to call it. It's just whatever phase you want to use. Same phase, where we kind of just absorbed omega m and omega naught into k. Okay, so we kind of brought that into k. So okay, now we can basically talk about a differential work element needed to move a particle by the restoring force f a distance dx. So dw is equal to negative f dx, which is just, if we plug in, f right is negative kx, so it's just negative makes a positive, so it's just kx dx. In other words, dw is equal to kx dx. Well, what do you do then? You integrate with respect to x. So we get work, basically, which is the potential energy, because that's equal to the potential energy. Well, that's just 1/2 kx squared. And that's a formula you're probably very familiar with, which is the same thing as 1/2 k a squared sine squared omega naught t minus phi. Okay. So now we can basically combine for the total energy, right? Where the total energy of the system is always the kinetic plus potential. So E is equal to T plus U, which is just 1/2 k a squared. And we're going to be using the more general form of the cosine squared omega naught t minus phi plus sine squared omega naught t minus phi. Well, lo and behold, this is all 1. In other words, it's just equal to 1/2 k a squared, which you've probably seen in your lower division classes, that the total energy is equal to the maximum amplitude squared, right? Like the maximum potential energy you have. Good. Now we can define the period of motion in such a way that, since we have the frequency, right, the frequency is omega naught. If we multiply it by the period t naught, we should get 2 pi, because that's the period of a sine wave, right? In other words, that tells us the period of motion is equal to 2 pi over m over k, right? Because omega naught, again, is square root k over m. Okay. Excellent. So again, omega naught then. Omega naught is equal to 2 pi. They use v, the frequency. I always use f, but whatever. Is equal to square root k over m, which I kind of already said. And then v naught, which is the frequency again, I use f, normally is equal to 1 over 2 pi square root k over m. And these are just the definitions, basically, of period and so forth. But okay. And then they basically tell us, for many problems, simple pendulum being a great example, you'll get more complicated expressions. In terms of, like, instead of just getting an ordinary differential equation like this, where it's very simple, you'll get maybe like a sine or something, or so forth. Like for simple pendulum, you could get theta double dot plus omega naught squared sine theta is equal to 0. And then you can basically make the small oscillation assumption. Assumption, which allows you to take the sine and basically do a Taylor expansion of that, and then you basically get sine theta is basically theta, and then boom, sine theta is basically theta. Well, then we just have x double dot and x again, and you get the answer again. And we can see what happens when we can't make the small assumption, and you might have to solve this problem a different way with maybe like a Lagrange formulation or something, but we'll get into that later. But anyways, okay. They give us an example of, let's see, find the angular velocity in period of a solid sphere of mass m. So example 3.1. Okay. So we know I for the solid sphere is 2/5 mr squared. Okay. Using the parallel axis theorem, we basically get 7/5 mr squared, because we're trying to go for a different axis. So let me show you a picture of what I'm talking about. So sphere, right, around the center, 2/5 mr squared. We want to move the pivot to here, 7/5 mr squared. But okay. So what we can basically do then is we know the torque, or the force of gravity, first of all. So let's write all this stuff down. The force of gravity pulls the sphere back towards the equilibrium position as the sphere swings back and forth with an angle theta. So we have our force is equal to mg. We know our torque is equal to I alpha. Alpha is theta double dot. So for small oscillations, we have n is equal to, for oscillations, n is equal to rmg sine theta, which is approximately rmg theta if theta is small. small oscillations, right? That's kind of what we're just talking about. So then that immediately tells us then that I theta double dot, so I alpha is equal to negative R mg theta, right? Torque is equal to I alpha. And the reason why it's negative is because as theta increases, theta double dot is negative. So as this gets bigger, right, the torque wants to basically bring it back. So we need basically to solve this equation, which just tells us theta double dot plus R mg I theta is equal to 0. Well, what do we know? This right here is just the constant, right? So that just looks like all of our problems before. So that's kind of our like constant omega naught squared, right? So that tells us omega has to be equal to square root R mg over I, right? Because this looks like x double dot plus omega naught squared x is equal to 0. Same equation, so pattern matching. So if you plug in your values, you get 5g over 7r if you plug in for I. And then we can immediately get our period, which our period is equal to 2 pi square root I over r mg, which is just equal to 2 pi 7r over 5g. And then boom, we solve for the period and frequency simply by pattern matching. So good. But now let's move to 3.3, where things get a little bit more complicated, where we have harmonic oscillations in 2 dimensions. Okay. So now we can basically define, instead of f is equal to negative kx, we can define f as equal to negative kr, where r is now a 2-dimensional vector. And then we can resolve it in polar coordinates as f of x is equal to negative kr cosine theta, which is just negative kx, and then f of y is equal to negative kr sine theta, which is just negative ky. So therefore, we have 2 equations of motions, right, for each of the force equations, which just look very similar, right? Omega naught squared x is equal to 0, and y double dot plus omega naught squared y is equal to 0. And as before, remember, omega naught is k over m square rooted. And then basically for each direction, right, we just have like x of t is equal to, remember, pick your sine or cosine, does not matter, a cosine omega naught t minus some constant phase shift. Y of t is equal to just a different constant, but same solution, right? Same type of solution, I should say. Okay. So then we kind of have these equations, and we can kind of try to combine it in 2 dimensions. So we know that y of t, right? Y of t is equal to b cosine omega naught t minus alpha plus alpha minus beta, just from this right here, right? We're just basically adding and subtracting alpha, so we're getting beta. So it's just this equation right here. And that lets us basically expand this from the log cosines, or whatever it's called. B cosine, not log cosines, it's somewhat trig identity. I don't remember the name of it. But you just, it's like cosine, cosine minus sine, sine. Cosine alpha minus beta minus b sine omega naught t minus alpha sine alpha minus beta. We can define, let's define delta as just the difference between the 2 constants, alpha minus beta, and therefore we know that cosine of omega naught t minus alpha is equal to x over a. So that lets us now define y as equal to b over a, x cosine delta minus b square root 1 minus x squared over a squared sine delta. In other words, a bit of, what's it called? Substitution. And we get ay minus bx cosine delta is equal to negative b square root a squared minus x squared sine delta. And then we can square this and basically get b squared x squared minus 2abxy cosine delta plus a squared y squared, which is just a squared b squared sine squared delta from the identity. Perfect. So now what we can do is we can see what happens if we set delta, the phase shift basically. If delta is equal to plus or minus pi over 2, well then this just becomes x squared over a squared plus y squared over b squared is equal to 1. Now, that kind of looks like something. It kind of looks like a circle, actually, or an ellipse. But anyways, then we can set if a is equal to b, right? If a is equal to b, so if a is equal to b, this is just to get some intuition on what these equations are telling us. Then we have x squared plus y squared is equal to a squared. In other words, x squared plus y squared is equal to r squared. So you quite literally have a circle. Yeah, so if a is not equal to b, you get an ellipse. If it is, you have a circle. And that's how it works. Another special case is what if delta is equal to 0. Then we have b squared x squared minus 2abxy plus a squared y squared is equal to 0. Or, as you might realize, this is just, like the expansion of something squared. Bx minus ay squared is equal to 0. And then that tells us the equation of a straight line, or just y is equal to b over a x if delta is equal to 0. And boom. And if you do the same thing with phase of plus or minus pi, you get the same thing, just the negative sign. But anyways, let's just kind of see what happens in 2 dimensions for our oscillations with different angles of delta. So 90 degrees, right? We get our circle. Basically, every multiple of 90 degrees, you get a circle. Or, sorry, every other multiple, you get a circle. Or and then the other one's a line. And then we can kind of see how it's basically, how the oscillations change as the phase angles change. But okay. Don't really matter. Phase diagrams, I don't know how important those are, but I guess we can go over that. When I think of phase diagrams, I kind of think of material science, but I guess. Or like, thermodynamics. Also thermodynamics. But anyways, let's get into phase diagrams for 3.4, which tells us, so let's see. Let's see. I think the phase diagram basically tells you the different paths something can take depending on where you start from. And you can consider basically x and v, so x of t and x prime of t, to be the coordinates of a point in a two-dimensional space. We can call that the phase space. You'll see a lot more references to phase space as you take more physics classes. But basically, if you take all these possible paths, you get the phase diagram of the oscillator. So let's kind of unpack that. So again, we have x of t is equal to a sine omega naught t minus delta, and that immediately tells us, let's take the first time derivative. Well, that's a omega naught sine omega naught t minus delta, because delta doesn't matter. Or sorry, cosine. So we can eliminate t from these equations, and therefore we get x squared over a squared plus x prime squared over a squared omega naught squared is equal to 1, or aka this is an ellipse. Which, if we plug in for energy and stuff, using our, remember, amplitude equation, that E is equal to 1/2 Ka squared, right, total energy. That lets us rewrite this as x squared over 2 E divided by K plus x prime squared over 2e divided by m. And immediately we can kind of see O is equal to 1. And these are just a family of ellipses that kind of have a phase path that corresponds to a definite total energy of the oscillator. So different energies are allowed. Again, we're working in classical physics right now, so this kind of allows us to have a continuum of energies. But in quantum mechanics, you would kind of see, like for a quantum mechanical harmonic oscillator, if you looked at the phase diagram, you'd see quantization of energy. Okay. Let's see. A note that they make in the textbook is no two phase paths can cross. And the reason being, if they would cross, that would mean basically that for any initial conditions, the motion could then go across different paths. So if you have different initial conditions, it would not describe a unique set of a phase path, and that would violate basically the fact that a solution to a differential equation is unique. Okay, so basically, how do we get these equations and so forth? Well, let's go back to our original equation, right, which is x double dot plus omega naught squared x is equal to 0. Well, that's just, remember, d squared x over dt squared. That's what that's shorthand for. Plus omega naught squared x is equal to 0. Well, we know dx dt is equal to x dot, and dx dot dt is equal to negative omega squared x, right? So we can divide these equations by the first equation, and we can get dx dot over dx, right? To get rid of the dt's is equal to omega naught squared x over x dot, like that. Now this is a first order differential equation where x dot is equal to x dot of x, and the solution is just a circle, x squared over a squared plus x squared. These families of solutions, or this is the solution to that. Sorry, I'm sorry. This is the solution. This is the solution. In other words, for the simple harmonic oscillator, we can basically get the general solution two ways. One of the ways is, as we saw earlier, just solve the second order differential equation much easier. But the other way is we can kind of try to solve it through the derivative of it and find the equation of the phase path. In other words, x prime is equal to x prime of x. And it's much easier than just solving x of t is hard a lot. And this is why you go to phase space. This is why phase space is so useful, because a lot of times it's really hard to solve a problem directly. And it's why another good example of this is in electronics and stuff, when you're trying to solve for, I don't know, like the time varying parts of your circuit, you want to go to Laplace. You want to Laplace transform your stuff. But anyways, okay. Let's move on to damped oscillations, where things get a little bit more interesting because we get a more interesting differential equation. And if you're really good at differential equations, none of this stuff is really a problem. It's kind of just a bunch of math. But physicists don't really like math, so we try to figure out tricks for it. So damped oscillations, imagine we have basically a resisting force. So we have mx double dot, remember, just ma, plus now some resistive force corresponding to the derivative of x, plus kx is equal to 0. So what this kind of looks like is like if I had like a graph, instead of just a normal sinusoid, right, I would instead get some damping curve like that, and we'll see exactly where this comes from. So I'll draw it in blue. So instead I get like this, you know, so it's like damped. I kind of drew it pretty bad, but you get the point. Why I know that is because I kind of cheated, I know. But what we can do is we can rewrite this as divided by m x double dot plus 2 beta x dot plus omega naught squared x is equal to 0. Where again, omega naught squared is just k over m, and then 2 beta is b over m. But okay, so beta again is defined as b over 2m, which is the damping parameter. Okay, and these are just very famous and important class of second-order differential equations. Now, the roots of this equation is R1 is equal to negative B. And the textbook basically explains the math for you, but we don't really care about the math because we're not mathematicians. We know if we have a hard math problem, look it up online or ask your friendly neighborhood mathematician. If we want the general solution for this, we have x of t is equal to e to the negative beta t, a1 e to the b squared minus omega naught t squared plus a2 e to the negative beta squared minus omega naught squared t. So these are very fancy equations, and there's 3 important points of interest. But before I get into these, I just want to kind of make sure we're on the same page. In other words, why does this make sense? Well, let's look at this equation right here, right? This equation right here is basically telling us we have an x double dot, we have an x dot, and an x in the equation. In other words, x, you take the derivative of x, it has to return itself immediately. So we cannot use sines or cosines. You can with the sum of them, but not important. In other words, we need something that's more general than that. What's that like the derivative of is itself. And the only real thing that does that is e, right? It's 5 like e to the x. What's the derivative of e to the x? It's e to the x, right? D e to the x dot, or e to the t, sorry. Like that. So we basically need an exponential. And the reason why it's decaying, we'll see from the math. But okay. So there are 3 general cases that really matter, which we can kind of see from the equation. So let's see what happens if omega naught squared is greater than b squared, right? Because, oh, by the way, the t's, I should probably be a little bit more careful about how I write this. The t is outside of the square root. I need to make that clear. T is outside the square root. Same here. So if omega naught squared is greater than b squared, imaginary, right? Same story here, right? In other words, we have an underdamped region. You'll see why it's underdamped. Is when omega naught squared is greater than beta squared, because then it's imaginary. And we have critical damping. So something that's critically damped, right? Omega squared is equal to beta squared. Well, that means that just goes to 0. That goes to 0, and you're like, oh, great. Now I just have basically a normal answer, right? Like something we've seen before. Okay? And then we have overdamped, where omega naught squared is less than beta squared. So it's real. So underdamped. Let's do underdamped first. Underdamped. It's useful to define omega 1 squared as omega naught squared minus beta squared. In other words, we define a new like fundamental frequency basically, where this is greater than 0, right? Because we defined it as this. Okay, that lets us rewrite our stuff as x of t is equal to e to the negative beta t. Again, a1 e to the I omega 1 t plus a2 e to the negative I omega 2 t. Omega 1, sorry. Omega 1 t. Where the I comes from the fact that you have a negative root 1, right? And now this right here is this right here actually is just a cosine. If you look at Euler decomposition. So x of t is equal to a e to the negative beta t cosine of omega 1 t minus delta. And that's why we like those imaginary exponentials, because it allows us to get back our cosines. Where you can look up on Wikipedia or whatever how to get sine or cosine. Cosine is the addition, sine I think is the difference between them. Divided by 2. But yeah. Okay, so we call the omega 1 the angular frequency of the, oops, 1, not I. Angular frequency of the damped oscillator. Okay. Excellent. And what we can basically say is that if omega 1 is less than omega naught, if the damping is small, then we basically say omega 1 is equal to square root omega naught squared minus b squared, right, from our definition. And that's almost just omega naught. So angular frequency can we use, but it's not actually true unless if beta is 0. Okay, now the maximum amplitude that we can get, again, is just x is equal to, max basically is equal to plus or minus ae to the negative beta t, right? Because we have this decaying exponential right here, that's actually what I drew in the red over here. I kind of cheated because I knew the answer. But okay. Let's look at a graph of the underdamped motion real quick. Just so you guys can kind of see what I'm talking about. So we see the decaying exponential there, and here's our normal sine wave, and the dotted line right here, right, like that. And our actual answer, right, is like that, because we see it gets damped by that real. Because remember, imaginary exponentials are sinusoids. Or harmonics, sinusoids basically, and what's it called? Real parts of stuff can damp it basically. In other words, that's what's damping it, or attenuating your signal if you want to call it that. Okay, now we can find the ratio of the amplitudes of the oscillations by this equation here, where we find t as the period. As it's the time basically when you have the pair of maximums, and yeah. And I guess your beta t1 is known as the logarithmic decrement of the motion. Not super important. What's important is that you realize that your signal gets attenuated like this. But okay. Let's ignore the first one. Before we go to critically damped and overdamped, I do want to show this one picture because I think it's really cool. Just so you can kind of get an intuition of what's really happening. This is kind of all three of them, the three cases of damping. So again, underdamped, right, is this really cool one that we just talked about, like that. Critical damping, we notice that the effect is much more drastic. But then when you overdamp it, notice it's almost like linear to a certain extent. It's just like so let's look at what the equation was, right? The equation was mx double dot plus, or I guess it's x double dot plus 2 beta x dot plus omega naught squared x, right? In other words, what this is saying is if beta is really big, right, this linear term dominates, okay? And we're getting basically just a line. When it's critical, it's kind of a mixture, and it's kind of just the exponential, really. Or it's kind of a mixture of both. And then when it's underdamped, well, you're just looking at basically a sinusoid that's kind of like changed. So if you looked really close, like just zoomed in on this piece right here, zoomed in on, if it lets me switch to a pen, there you go. So zoom in on this piece right here, it just looks like a sine wave. You can't really tell unless if you look at it over a longer period of time. But yeah, okay, good. Let's move on to the next one, which is critically damped. So critically damped is probably the easiest, I think, to understand, because remember, beta is equal to omega, or the squares of them are equal. So that lets us basically get the roots of the function immediately, because we know x of t now is just equal to a plus b e to the negative t, right? Because the other exponentials cancel out in this equation right here. Because e to the 0 is 1, right? Okay, so now that we have that, we basically see the curve right there for critical damping. It's just basically the exponential plus some constants that it does vary with time. Anyways, okay. Now, overdamped is probably more interesting. Because beta now is even larger than omega naught, and we get too much damping basically, right? So that immediately tells us x of t, again plugging in the same equation, is equal to e to the negative beta t. So that's our, again, decaying factor kind of, and that's a1 omega 2t plus a2 e to the negative, oh, I forgot the e here, my bad, I apologize. E to the omega 2t, I'm trying to read my text at the same time, sorry, omega 2t, where again, omega 2 is a little different this time. It's b squared minus omega naught squared. That's why it's not omega 1. And omega 2, again, is not the angular frequency, because the motion is not periodic, as we saw for this is like basically a line, right? It's not periodic at all. But in the underdamped region, right, it's kind of a sinusoid or periodic, but it's being attenuated. But okay. So this basically lets us realize that the overdamping results in a decrease of the amplitude to 0 that may have some strange behavior on the phase diagram. So let's look at what they mean by that. So let's look at, we're plotting again x dot by x. Okay. So again, it's like, remember, it's x dot is equal to x dot of x, right? It's like that. That's kind of what we're working with right now. And if we look at the first case, right here, right, x dot is greater than 0. So that means x of t reaches a maximum at some t greater than 0 before approaching 0. In other words, we reach a maximum before we get to 0. Okay. And then the velocity x dot decreases, becomes negative, and then approaches 0. So if we trace it out, right, it goes wee past 0 and then back to 0, right? That's what we kind of see. But in the second case, right, right here, x dot is negative. So it basically wants to approach 0 back. And then in the third case, they're given by, what's it called? We basically have these curves, and they're kind of shown below in the third case, where since it's also really negative, it kind of rebounds back, and we kind of see a repeat of what was happening. And you can kind of think it's oscillatory, because it's kind of like, you know, like that, if that makes sense. But okay. Don't want to be pendulum. No, let's skip pendulum for now. Okay, let's get to 3.6, and we'll probably end after 3.6. I don't really know how much is left after 3.6, but 3.6 is sinusoidal driving forces. Okay. So, we've talked about damping. We've talked about the simple harmonic. Now what happens if we add a sinusoid to it, right? So we have f is equal to negative kx, harmonic, minus bx dot, our damping, plus, let's say we have some extra force, f naught cosine omega t. It's a sinusoid, though. Okay, well, let's again do the analysis. So that tells us mx double dot plus bx dot plus kx, normal, is not equal to 0, but is equal to f naught cosine omega t. So we no longer have a homogeneous differential equation. But this lets us now tell us that x double dot we divide by m is plus 2 beta x dot. So all the same analysis, right? But how does a sinusoid change it? In other words, how does a non-homogeneous differential equation work? So if you're really good at math, you could just solve it and just do it outright. But I'm not exactly amazing at math. Where a, by the way, is equal to f over m. F naught over m, sorry, where f naught is the amplitude of the force. Basically, we have, here's the general solution again. It's the exact same solution as the homogeneous solution, but we need to basically try to fix it now. So how you solve non-homogeneous differential equations is you kind of solve the homogeneous one first, and then you try solutions to fix it. So that's what x complementary, the complementary function is, and the particular solution is. which makes the right side. In other words, this is our left side, which is our ordinary homogeneous differential equation, and this is our right side, which is our particular solution of a cosine omega t. So we can substitute into our equations, and we get this, and we can expand cosine of omega t minus delta and sine of omega t minus delta, and this is what we get. And now we also know that sine and cosine, right? It's the same thing. It's sine and cosine, the same thing, right? If we look at it, they're linearly independent, right? And that tells us then that basically this can only be satisfied in general if the coefficient of each term vanishes at the same time, or else you'll never have it equal 0, right? Because sine and cosine are independent. So these two will never, give you 0 at the same time, right? That's kind of the point. So that immediately tells us then that from the sine term, right, tangent of delta is equal to 2 omega beta over omega naught squared minus omega squared, or that this more complicated expression. Okay, and then that means we can solve for d, and we get d is equal to a over omega naught squared minus omega squared cosine delta plus 2 omega naught beta sine delta, which we got d from substituting into here. Okay, and that's kind of the general way of solving a non-homogeneous differential equation. Is you need a complementary and particular solution. But okay. Now, that tells us that the particular integral is, remember, just our xp of t, where we just plugged in our value for d, because this is our value of d, because it was d cosine omega t minus delta, and then remember delta is this right here. Okay. So the general solution, again, that's why we have the complementary and non-complementary, is x of t is equal to x complementary of t plus x particular of t, where left, right side. So this is our cosine whatever, and this is our other one, our our homogeneous differential equation, second order differential equation. Homogeneous just means equal to 0. It can be written as equal to 0. Okay. So now that we know this, let's look at basically some pictures to see what's really going on. So this is like really complicated math, not the pictures, but what we just did, which is kind of a pain to solve by hand, but that's why we have mathematicians or computers. But okay. So here we see some examples of sinusoidal driven oscillatory motion with damping. So beta 0.15, we see a very slight damping, right? And then notice how the complementary solution looks versus the particular solution here. And then notice what happens when we add them together, which is what we actually get. In other words, remember the particular solution is just a cosine, right? If you look over here, it's just number. We don't really care about. This is just a number, right? Times a cosine, right? So in other words, cosine has some amplitude, whatever. And then our particular solution, right, is like our little our complementary solution is like our damped oscillator, right? And then we add them together and we get this weird phenomenon. Where you notice, like, if you're trying to analyze this, if you just saw this right here, you're like, oh, that's a sine wave, right? It's actually not. It's a lot more complicated than that. But yeah, it does reduce to a sine wave once this goes to 0, right? Okay. And then we see in this case right here a different example of the same thing. But okay. But let's find out some resonance phenomena. In other words, what happens when... Actually, let me just write down. Resonance phenomena. In other words, what happens when omega r, omega resonance, we find d at max, basically. What's the omega at d at max? We want d omega when omega is equal to omega r is equal to 0 to find the maximum, right? And if we differentiate our value for d, that we get omega r is equal to square roots omega naught squared minus 2 beta squared. Okay. In other words, the resonance frequency omega r is lowered as the damping coefficient is increased. And this should kind of make sense because if we have a super high damping coefficient, you don't really expect to have a high omega naught, right? You're not going to get a lot of these fast, right? These oscillations fast because it's being damped. In other words, being slowed. So it doesn't want to move towards those and change directions. But okay. Now we can compare them. So let's just compare them really quick. So we have basically three situations, right? We have free oscillations, no damping, where we have omega naught squared is equal to k over m. Free oscillations, we have omega 1 squared is equal to omega naught squared minus beta squared with damping. Driven oscillations, with damping, we have driven oscillations, we add a sinusoidal force as well with it. So omega r squared is equal to omega naught squared minus 2 beta squared. Noting that omega naught is actually the maximum. So omega naught is greater than omega 1, which is greater than omega r. Okay. Now we can define the quality factor, which you've probably seen in a lot of different cases, as omega r resonance omega divided by 2 beta. You might have seen this in circuits or whatever, but basically the quality factor is intimately related to, if I have a graph like that, it's intimately related to the bandwidth right here. And HK, the higher the quality factor, the smaller the bandwidth you have. In other words, if you have an infinite bandwidth, you basically get a delta function. Q equals infinity, that's what you get. But okay. Let's look at some graphs. Just to kind of, because my artistic my drawing's not good. But okay. Where here's kind of what I was drawing, d versus that, and here I guess is delta versus omega. Or we see again how Q changes. But okay. Yeah. Now, the values of Q depend on a lot of things. You have the quality factor of components, blah, 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 a bunch of stuff. But in the classical picture, we can also talk about radiation damping, which basically tells us how radiation changes with distance, I think, or time. Or like the sharpness of spectral lines. Because, as we know, like, you guys might have heard in other classes, like stuff like black body radiation, right? Like the sun, we can model as a black body, it radiates energy or whatever. With like Stefan Boltzmann's constant, like sigma t to the 4. But that radiation, right, it's not like all this energy hits us over here, right, on Earth. It's actually damped. So like if the energy was modeled as like some value like that, well, it's actually like we get it like that because it's damped. That makes sense. But okay. And the radiation width, we can basically model it as an oscillator with a Q value, which is apparently approximately 5 times 10 to the 7. That's a really big Q value. Stuff in circuits, like depending on how small you go, is like 20 or something. Is a pretty good Q value. But anyways, we can calculate the frequency for the kinetic energy resonance by basically find out what x prime is, right? Because for kinetic energy is 1/2 mv squared. We need x prime, so we just, same equation, it's our d value, but just find the derivative of it. Omega naught squared minus omega squared plus 4 omega squared beta squared sine omega t minus delta. In other words, we just added an omega and made it a sine function from our original equation here. Okay. So we can continue with that, and we just, wrong Let me just screenshot the rest of the page so I don't confuse you with my poor handwriting. But basically what we have here is we have the kinetic energy, so it's 1/2 mv squared, and they just plugged it directly into this. And they just squared the x prime equation here. And then we can take basically the average of it, and the average of a sine is basically just 1/2 for any sine. It's sine squared, sorry. The reason being, if you look at the sine function, right, if you take the average of a sine, it's 0 because it's above and below the same amount from to infinity, basically. You can kind of see how they do it here, actually. Over one period, same thing as infinity. But if you square it, right, you just get, that's sine squared. That's what that looks like, and you can deduce that it's 1/2, graphically, geometrically, or you can just do the math yourself. But okay, enough said. Okay, and then we basically get that where omega, or in other words, where t is maximum, we just take the derivative and we get it. And if you take the derivative for omega equal to omega e, in other words, the maximum kinetic energy, we find out that omega e is actually equal to omega naught. In other words, omega naught is the natural frequency of the system for undamped installations, and we find the kinetic energy resonance occurs at the same frequency. Okay, good. Let me see how much longer is in the chapter and see if I want to. I don't know if I want to go into Fourier series. That might be a lot. I'm not going to do 3.9. That's too much work. It's optional. Let me see if that's it. I can finish it, I think. I guess I will go into Fourier series. I have 10 minutes. I'll do 10 minutes more. So, let's see where we're at. We'll skip that for a second. So let's go to physical systems real quick, 3.7. Physical systems. Stuff like a mass spring. And I guess it's basically just examples of stuff that happens. Here's a really good example. I like this example. I'm going to screenshot it so I don't have to write it out. But I talked a bit about circuits and how you can have Q factors and stuff, and this is just an easier example of an RLC circuit. So I guess they're not really showing you the derivation for it because you don't really need to know full circuit theory yet. But let's analyze it from our perspective. So we know the voltage across circuit elements is going to be across the inductor, right? It's L di dt, because remember, an inductor has changing current. Or in other words, L Q double dot. Okay, because Q, right, is equal, I is equal to dq dt, right? That's how we get that. The voltage across the resistor is just Li, which is equal to L dq dt, which is just LQ. And then across the capacitor, it's just the charge divided by the capacitance, right? Q over C. Okay, so we can write it as basically this if we run it with an AC signal of E naught sine omega t. And we immediately see our circuit problem just derived into an oscillations problem with damping being provided by the resistor, which should make sense, right? Because resistors dissipate energy. Inductors and physics and in engineering are modeled as basically perfect. Like they don't dissipate energy. Same with capacitors. So this is your sinusoid, and this is just your constant number. In real life, though, inductors are basically modeled as an inductor and an equivalent resistance, Req, but that's for another class. And then we have our driving force, which is E naught sine omega t. In other words, it's the same problem we just did before. So let me just screenshot, honestly, the page. I wonder if I'll get copyrighted for this. I'm not making money off this, but anyways. Okay. Again, beta is B over 2m, R is 2 over L. Beta is B over 2m, which goes to R over 2L, right? Because we're just pattern matching, right? Beta, R, M, L. Okay. Omega naught K over M goes to 1 over square root LC. Where this comes from is a good way of explaining a transfer function of circuitry, but not important. A, F over M goes to E naught over L. So in other words, everything looks identical, right? It's just pattern matched at this point. So we can basically find a solution for I, VL, and then we can take the derivative and basically find omega naught max as this function here. And then if we know that omega naught is equal to 1 over square root L, and the resonance charge frequency, omega R, is equal to square root 1 over LC minus 2R squared over L squared. In other words, we just change C for L. And that's what we get. But okay, enough about that physical example. There's more in the textbook, not super important. But now let's talk about the principle of superposition / the Fourier series. By the way, huge shout out to 3Blue1Brown and other YouTubers who have amazing videos on the Fourier series, principle of superposition, because there's a lot of really good resources out there if you want a visualization of the Fourier series. Sorry for my handwriting. But basically, the oscillations that we have been discussing can basically be written as this: some second derivative plus some first derivative plus some number times a function that's corresponding to t is equal to some other sinusoid function, right? In other words, the quantity on the left side, right here, this right here is a linear operator. Derivatives and higher order derivatives are linear operators. In other words, we have some linear function, the linear operator, I'll put a hat over it so you know it's an operator. X of t is equal to our f of t. Okay, now from the principle of superposition, it tells us that an operator, if it's linear, obeys linearity. So x1 plus x2 is the same thing as linear operator on x1 plus linear operator individually on x2. In other words, we can pretend they're not there and then just add up all the solutions and get the actual answer. So that tells us that we can set linear of x1 equal to f1 of t, linear of x2 equal to f2 of t, and then we just add the two equations up together. Another good thing about linear operators is constants, scalars don't matter. Like, they just work how you would expect them to, like that. Alpha 2, f2 of t, like that. In other words, they just work how you would in like normal addition or whatever. But okay, that immediately tells us then that linear operators over in the more, I guess, general form, what I just wrote is like this. So we can basically now define linear combinations then of just x of t and f of t. Okay. And if we say each of these individual functions has a simple harmonic dependence on time, like cosine omega t, then we know that our solution, right, is just a sum of a bunch of cosines. So if every single one of these is basically just some kind of sinusoid, our solution then for the more hard case is just a bunch of cosines, right? We can just add them all together. Now for a steady state solution, for x of t, right, because x of t is more complicated, this is just a bunch of forces that are all cosines, right? If we look at the right side, it's basically our d value times our cosine, right? And that's what we get. We see it's just a sum of that. And then we define phi of n as before, like this, where again, omega n is just, it's dependent on the one you're doing in the sum. So, okay. In other words, that tells us a Fourier series is basically an infinite sum of all your sines and cosines in order to represent whatever type of motion you're going through. Okay. Now we know that our f of t is periodic, so f of t plus tau, where tau is the period, is just equal to f of t, right? So that immediately then tells us that f of t must be 1/2 a naught constant plus a superposition of cosines and sines, because it's periodic, where we can define a of n and b of n as 2 over the period, so it cancels out, 0 to the period of basically f cosine n omega t, ft sine omega t. In other words, that's how we solve for these. Basically, oh Jesus, and you can replace the integral limits with, just by doing a substitution, pi over omega, negative pi over omega, because what's it called? It has a period of t, right? In other words, if it has a period of t and the function's periodic, anything here that has length t should give me the same integral, right? Like, just think about what you could do with sine, right? If this is a period right here, if I add this right here, it's the same as if I can extend this and I add, put it in red, add this right here, right? It should give me the same sum because it's the same period. Okay. This is kind of a very, very quick overview since I need to leave. But basically, Fourier series are very useful ways to solve stuff and find a general representation of periodic functions. But okay, they have a bunch of examples of it, but I don't think I'll go into the math too deep because it's kind of more so for a math class. We'll see if I need to for a problem later on or whatever. I'll explain that more in detail. But yeah, thank you for watching. Sorry for going kind of quickly at the end, but yeah, Fourier series are very important, and there's ways to like the way you solve this isn't terrible. You just plug it in. The reason why it works is because of independence, and you realize there's like a delta function and stuff cancels out. But okay, I was about to say thumbs if you loved it, subs if you loved it. Anyways, that's it for chapter 3. I will be going over I'll be skipping chapter 4. I'll probably going over chapter 5 tomorrow. Okay, bye guys.